Alrighty, so I passed out quizzes. I thought generally we did a good job. I think it was only at one group that had some misunderstanding of what we were asking in terms of order. I think I saw them trying to give definition of a subgroup. So that messed up problem 1 and 2, which is like half the problems on there where you get no credit. So just be really mindful of your definitions. Those are going to be our most important pieces here. Without our definitions, we're not going to be able to do many of our problems. So just be super careful about that. But I thought otherwise, we did a good job. Some small details here and there that we can be more careful for the midterm. The one thing I didn't see anybody do, so I didn't take off points on anyone's quizzes for, was what happens if we don't have a power, so that G to the N gives me back the identity. We have to make sure that we define that within our definition for order, because if I don't have an N, then what do I do for those other group members? Right, I need to be defined for every single group element. So I want to decide what happens in those cases, and that's exactly where we have our infinite order there. And then in terms of our theorem for our one-step test, a lot of us were really close in those, but I think at least half of us forgot to say G needs to be a non-empty subset. So make sure you've got all your assumptions in there, because if you don't, you'll might by accident not show those pieces when you're actually trying to prove them. So be mindful of that. Solutions are up on Moodle, so if you have any further questions, you can look there if I didn't give you enough comments. But feel free to come into office hours if you have specific questions on the quiz. Okay, so last time, I made a note about homework 4. There was one problem I just wanted to edit, was number 4. Or not number 4, but the problem about the number of distinct cyclic subgroups in U30. I wanted you to count how many you had, and then I want you to actually spell out explicitly which ones do you have there. So just make sure that you answer that piece of it. We'll quickly go over some of these pieces that we did last time, and then we'll work on our cyclic groups chapter 4 part 1. That's all the information that you need to be able to complete homework 4. Is that number 4, number 3? Homework number 3.
It's problem number 4.
Oh, okay, that's where that's coming from. Okay, so in homework 3, you should be able to answer one of the 2 cyclic group problems. You shouldn't be able to do number 2 quite yet, but after today's class, you should be totally fine to be able to do that. We will continue working on chapter 4 materials, cyclic groups. There's a lot of information about cyclic groups. That's what this next packet is on. We're not allowed to use any of the results that we learned from that new chapter for our old homework. The only thing we're allowed to use is that cyclic subgroups part 1 that we got last time that we didn't actually get to last week. So just to be clear there. Okay, so the last things that we did was we defined these specific examples of subgroups that we get for any group G. We already talked about our cyclic subgroup, which is going to be the things generated by elements inside of your group, where we'll use our angled brackets to denote these cyclic subgroups. These are going to be the things that look like a to the n, where n is any integer power. Okay, and what we'll actually do today is we'll prove that we do actually get a group in those cases, or did we, unless we proved that already. No, I think we actually did prove that already. So we already know that these do actually give us back groups, which is why we call them subgroups here. We also talked about our center, our ZG, which are all the elements in your group that commute with everything else in the group. Versus the centralizer. Again, these are similar definitions, but they are really different. This is going to be the centralizer of an element in the group, which we'll denote as C sub G for the group, and then A for the element. These are going to be all the things in your group that, in particular, commute with the one element A, right? I don't need it to commute with everything, just specifically with that element A that I'm writing in my parentheses here. So the notation kind of helps you to decide which one am I actually looking there at? Am I looking at the center, the centralizer, the things that commute with the entire G, or just specifically with little a? I do have to specify what the group is, because I could have shrunk the group, and then my sets here would look a little bit different. Okay. It turns out that all of these give us back groups, and we have these specific containments, the things that commute with everything in the group, in particular, are going to commute with a specific element. So I know I'll get this containment here. What we also know is that the powers of A all commute with each other. So in particular, they're going to commute with A as well. Although I might have more things that commute with A other than powers of A. Something else that we pointed out is that these cyclic groups are all going to be abelian. They're all powers of A. It doesn't matter which order I'm manipulating these or multiplying these. I will get back the same exact answer. And then one thing that I think I mentioned, but I just want to re-emphasize, this will be helpful in the homework, is what if we figure out that for A, an element of a group, if the cyclic group generated by A has the same order, so the same number of elements as G, what can I say about my group G? G is a cyclic group, and in particular is exactly that cyclic group. Okay, this might be conditional for these numbers to be finite. I have to think a little bit closer, and I don't think that this is true, that for infinite sets or infinite groups, that this is going to be the case, that if you find an infinite ordered element or infinite ordered cyclic group, that they'll give you back the same sets. Infinities work a little bit weird with our groups. So in particular, this is if you're working with finite groups, then if I find that the group generated by A, the cyclic group generated by A, has the same exact size as G, they have to be the same exact group here, right? I also know one is contained in the other. And so if I know I have the same exact elements and one is contained in the other, they do actually have to be the same exact size if I'm working with finite orders here, finite number of elements. So I think this will be most helpful in that last problem that you'll have on the homework set. So just keep that in mind. Okay, so let's look at our properties of our cyclic groups. Again, this is the only thing that you'll need. For homework 3 that we haven't already seen. So the next packet that we see, we're not allowed to use for homework 3. It'll just oversimplify the work that we do there. So we want to make sure that we're not using things we're not supposed to. Okay, and so again, our cyclic subgroups are always going to be abelian. So sometimes we'll use our additive notation because usually when we're using addition, the way that we know it with like matrices, with real numbers, that's always going to be commutative. So usually when we think abelian, we think addition. When we think multiplication in terms of matrices, that's not going to be commutative. And so we don't always use that notation. In either case, we want to feel comfortable using both notation, the additive, which is when I would write that n times a, meaning a added to itself n times, or the multiplicative notation where I write a to the n, which means multiply a by itself n times. And we have these written in two different forms. Here we have our set builder notation, where I'm taking all my elements in my group G, so that I can write them specifically as A being added to itself some number of times, or if I'm using multiplication, A being multiplied by itself some integer number of times. The other notation just makes it easier for us to recognize what form do all of these elements have. It's just going to be A added to itself some number of times. But when we're showing things with like subgroups or we want to use a definition, that set builder notation is really going to be the most useful. Okay. And it turns out that these cyclic groups end up being the building blocks for all abelian groups. We'll get to that eventually, how to see if I have an abelian group, how can I rewrite it so that it really looks like cyclic subgroups in its pieces. But we'll get into that much later. Right, so our goal is going to be to understand abelian groups better. So first we have to understand the building blocks better, which is our cyclic groups here. Okay, can you guys think of any examples of cyclic groups that we've already seen? You're saying our UN? Okay, do we know that all of our UNs are cyclic? No, this one we don't know for sure. So this group under multiplication mod n, I can look through my entire list of elements. I can decide what the orders of these are. I can see how many elements I have. I don't always get the same number of elements in my UN as the order of my elements that I have there. So this is not always going to be true. There will be some n where I do get a cyclic group back, but I'm not guaranteed that every time my UN will be cyclic. Can we think of another example? Mm-hmm. Yep, so our trivial group, and I won't include that, but in our list. But the trivial group here, how can I write that as a cyclic group? What is it generated by? So I need it to be generated by one specific element, just by E. All the things that are in my set are really E being multiplied by itself some integer amount of times. If I multiply E by itself, no matter how many times I do this, I always get back the identity. So these really are the same. And my trivial group will give me back a cyclic group. Okay, any other examples? Yep, so we could have our rotations. Under composition, this is cyclic. Right here, we can think it's gonna be generated by our smallest rotation. So rotation by 360 over n. And usually we go clockwise. Okay, so here I can really think of this as all the powers of R. Where how can I think of my identity as a power of R? R to which integer power? To the 0 power. Okay, and here, where do I stop before I have my repetition? N minus 1. Right, so here we're seeing the order of our rotations of this group is going to be exactly n. I have power of 0, 1, all the way up to n minus 1. So in total, I have n elements here. Right, and really every single element here, I can write as R being multiplied by itself some integer amount of times. Okay, any other groups that are similar to Rn? Not exactly the same, but work similarly. Say it louder.
I'm thinking of the Deaton groups, but I don't think that.
So that one is not going to be cyclic. Right, if I use one of my rotations, I only get a rotation back. If I use one of my flips, I only get 2 elements back, the identity and the flip itself. So there's no way for me to use one single element to get back all my dihedral group. What's the nicest group that we know that we learned in 311? Our Zn. So these are going to work almost identical. And is this under addition or multiplication? Under addition. Under multiplication, we don't necessarily get a group because we don't necessarily get inverses for all our elements. Specifically 0, I know for sure will not have an inverse. And what is this generated by? Which element? By 1. Okay, here I want to remember I'm adding, that's my operations addition mod n. So I really want to think, I want to add 1 to itself some number of times until I get back all of Zn here. So here I can think, right, the things that look like k times 1, where k is some integer. But that's really saying add 1 to itself k times. Okay, and so I'll have the elements 0 up to n minus 1. So again, I get n elements here. So essentially, these groups really look the same. One's multiplication, one is addition. It turns out with cyclic groups, these are actually pretty simple. We'll see that just knowing the size of their group will give us the full information about which group we're working with. Essentially, these groups are identical. If I just relabel the elements and relabel what my operation is here, we'll get into that much later when we think about group homomorphisms, maps between our groups that preserve their operation, that preserve their group structure. We'll see if I have a bijection that's also a group homomorphism. Really, those groups are exactly the same. I just labeled them differently. And that's what we'll see for our RN and our ZN here. Was that a hand?
Really quick question. So why are we doing it clockwise now? Because the previous, I don't know what's the difference between step chapter 1.
So if I said counterclockwise earlier, let's just go with counter. Off the top of my head, I couldn't remember which one I said. As long as you just fix one, right, that it should be totally fine. Oh, I don't care either way. You do it the way that you like it. And again, if you pick any flip that you want, the structure is always going to work exactly the same. It turns out it doesn't matter if I choose clockwise or counter. If I choose the vertical flip versus some diagonal one, the structure is going to be the same. You just want to be consistent in whatever problem you're working in. Yep. So I'll put counter / counterclockwise, whatever you want to use there. Okay, so right, we mentioned earlier that we thought UN might be, all of those might give us back a cyclic group. So I'm actually going to give you an example where it's not, just so that we can remember that this won't always work out. So if I'm working with U8, what elements do I have here and what operation am I using? 1, 3, 5, 7, under what operation? Multiplication mod 8 here. Okay, this is not going to be cyclic, and we'll see here why. So my goal, if I want to show something is cyclic, is I want to find one element that generates the entire group. So if I want to show something is not cyclic, I really need to show that none of my elements generate back the group. So we'll look through the powers of these elements, and really we can do this pretty easily. If I look at the group generated by 1, what elements do I get? Right, this is my identity element. 1 under multiplication is my identity. So if I multiply 1 by itself any number of times, I'll get back 1. Let's think the group generated by 3. I know 3 will be there. If I square it, what do I get? Okay, so I'm done. I just have 1 and 3 in my group generated by 3. So far I haven't found a generator that gives me the entire group, but I do need to look at the rest of them. So if I looked at the group generated by 5, I know I'll get back 5. And then when I square, I get 25, which is the same as 1 mod 8. Okay, I'll do the same for 7. And as you can guess, we're not going to get the whole group. If I square this, I'll get 49, which is the same as 1 mod 8. Okay, since none of these group elements generated back the entire group, I know that my U8 cannot be cyclic. Again, we did find some examples, I think maybe U10, where 3 did give us the generator, because we would get 3, 9, 7, and then 81 was 1. That gave us all 4 elements back. We can find examples of UNs where we do get cyclic groups back, but in general, we don't get this for free. So we want to be careful to not assume that we get a cyclic group here. Okay, so here, this is telling us that none of these give us all of U8. They're always going to give us some subset. Okay. And here I can say a little bit more. Every element here has what orders?
Less than 4.
Less than 4. In particular, has 1 or 2. 1 for the identity, 2 for all your non-identities. And the order of our big group here is strictly greater than 2. So if all my elements have order less than the group itself, that's enough for me to know the big group is not going to be cyclic. I can't find an element that will generate all of the elements in the big group. So it can't be cyclic here. Okay, so one first question that we want to be able to answer is under what circumstances will we get that different powers of A give us back the same exact element? Right, and eventually we're going to decide when will these as generators give us back the same group. So we'll first focus in on deciding when do I get repetition in terms of my powers? When do I know that A to the I is going to give me A to the J? What information do I need to know about I and J to know that I do get the same exact element here? That way I know in my set, I end up doing some repeating and I don't have to write the rest of the powers of A. I know where to stop. Okay, so that'll be our theorem 4.1, which we'll prove in just a second, but we'll need our division algorithm, so we'll remind ourselves of what that says. So if I have a group G and A an element, I have two possibilities. Either my element has infinite order or has finite order. We take care of these differently because these will give us different answers. So if A has infinite order, that means for every power of A, every integer power of A, I never get back the identity. It turns out we never get repetition, right? The only ways that A to the I, A to the J are the same is if the powers themselves are exactly the same, right? And every other case, if I and J are different from each other, I will get different powers of A, different elements inside of my group. Okay, that's not going to be the case when A is finite, right? We've been seeing these in our examples. When the order of our generator is finite, we do get some repetition that depends specifically on the order of the element. Okay, so let's say it has finite order of n. Then we get two pieces of information. We know that the group generated by A has the elements E, A squared, all the way up to A to the n minus 1. That means every power of A can be written as one of these elements, right? I don't have to write every single integer power because I will have repetition at some point. So I really only get n elements in my group of my cyclic group where A, the generator, has order n. But even more than that, number 2 is telling us when exactly do we get that repetition. And this just depends on the powers you're working with, mod the order of the element. So here the order of the element is n. So if I and J are equivalent to each other mod n, they give me back the same exact element in my group. Right, so I can write that in terms of divides. This is only going to happen if n divides their difference, but that's the same as thinking that I and J are going to be equivalent to each other mod n. Right, that was our definition of being equivalent mod n, is if the difference between those two values are equivalent to each other mod n, right? If the difference of those two give us back a multiple of n, right? Which is exactly what we've been seeing in all of our examples. I just need to look up to the power minus 1. And as soon as I go one step further, I've repeated, I got the identity, then I got the original element, then A squared, then A cubed, then A to the 4th, until I get back to my A to the n minus 1, and I start repeating again. Same thing happens if I go in the negative direction. I'll cycle in the same exact way. Okay, so our goal is going to be to prove this theorem entirely. So we'll do it in 2 steps, one part for number 1 and then another for number 2, depending on the orders. But again, we'll need our division algorithm to be able to do part of our proofs. So let's just remind ourselves what this says. This says is if I have 2 integers, A and B, they can be the same, they can be different. But in particular, I want B to be positive. So I don't want it to be 0 and I don't want it to be negative. Then what I can do is I can find 2 integers, Q and R, actually unique ones, Q and R, with the following property, that I can rewrite A as BQ plus R, where R is strictly less than our B value and at least equal to 0. So I'm going to get something 0 or positive that's less than my B. And I can really think in terms of division. So here, let's put this in our text here. If I want to think 7 divided by 2, 7 is going to be my A value, 2 is going to be my b value. So I don't want to be able to divide by 0. This is one of the reasons why we say b has to be strictly greater than 0. And I want to get unique q's and r's. This is another reason why we don't let b be negative here. Because if b could be negative, I could get 2 pairs of q's and r's that could work here. Okay, so really I want to think, how can I rewrite 7? In terms of a multiple of 2, I might not get something like a nice here. I could get a remainder. That remainder is really that r piece here. So here, how many times can I divide 7 by 2? Right, I can do it a whole 3 times before going over. So this will be the same as 2 times 3, which gives me back 6. Okay, but I have a remainder here of 1, which is between 0 and then the number that I'm dividing by here too. I can really think mod 10, my remainders are either going to be 0 or 1. They're either going to be odd or they're going to be even here. And if my remainder piece there was bigger, that means I didn't pull out enough of my multiples of 2, right? If I had done 2 times 2, I'd get 4 and I'd be adding 3. That's telling me that I didn't pull out enough 2's, which is why I didn't get that specific r that I wanted that was between my 0 and that b that I'm dividing by. Okay, but we'll use this in our theorem to rewrite some of our pieces to actually be able to prove the statement here. Okay, so we'll do the first part where the order of our element is infinite. And our goal is going to be to show that every power of I, where the powers are distinct, give us back a different element. There's no way that these are going to be equal unless the powers themselves are exactly the same. Okay, great. So if I have infinite order, that's telling me no matter which natural number I choose, if I raise it to that power, I can never get the identity, right? I can get the identity if I raise it to the 0 power, but if I plug in any positive natural number, really any natural number here, I can never get back the identity, or also have finite order in that case. Okay, so what we're going to do is we're going to think about what happens if we know that these powers or these powers of A are equal to each other. Our goal is to show that I and J have to be exactly the same. This is technically an if and only statement. So I have to go in both directions. But if I know I and J are equal, the backwards direction is going to be much easier to prove. Okay, so we want to think, what kind of manipulation can we do here to give us some information about our I and our J? We can multiply by the inverse of A to the J on both sides. And what would I get on the left-hand side if I did that? What mu power to A of A? I minus J. Okay, and I'll get back what on the right-hand side? Multiplying an element by its inverse will give me back the identity. And I know that these powers work really nicely, so I can just add my powers for the left-hand side. Okay, but I minus J, it's not necessarily, well, naturally, we can say is not going to give us back a natural number, because we just said for every natural number, we can't get back the identity if this element has infinite order. Okay, so what does I minus J have to be here? Yep, this is the only other possibility. This is either going to equal 0 or it's going to give me back a natural number, because I already said it doesn't give me back a natural number. It has to give me back 0. Okay, and this is the same as thinking I is equal to J here. So in the forward direction, we assume these powers give me the same element, and we show that the powers have to be exactly the same. Now we'll go in the backwards direction, and we'll assume that the powers already equal each other. But this is just going to be by definition of our powers, that A to the I has to give me back A to the J. Oh. So by definition, of powers, a to the I will give me back a to the j. Right, let's say I wrote I as a number 2 and j as 4/2, right? It doesn't matter how I represent that integer number. If I raise it to that same power, I should get back the same exact element. Right, if I didn't, then this would not be well defined, right? Then it would matter how I wrote these powers that I would get different results here. Okay, so that gives us the full story for the infinite order. That's kind of the easier case. When I have no power, no natural number power, that gives me back the identity. I know that the only way these elements will be the same is if the powers are exactly equal to each other. Okay, so let's look at our part 2, which is under the assumption that we're working with a finite ordered element. So let's say A has order n. Part A is wanting us to show that these two sets are equal to each other. So we would want to do this by double containment. And why do we know that this first containment we have for free already? By definition of which piece? Of our cyclic group, right? Our cyclic group are going to be all the integer powers of A. All of these are integers. They're not all of the integer powers, but they're a subset of the integers that are showing up as my powers, since I can write this guy's a to the 0. So this is really by definition of our cyclic group generated by A. Remembering that the powers come from the integers, and the ones that we're looking at here already have powers coming from the integers. So we get this one for free by definition. So if I want to show equality, the only thing I need to do is show the reverse containment. If I have something in my cyclic group generated by A, I want to show, I can write it as one of these n pieces. A to some power where the power goes from 0 up to n minus 1. Okay, so we'll take some j inside of my cyclic group generated by A. Again, our goal is going to be to show it's one of these n elements. So I can write it as a to the k, where k goes between 0 and n minus 1. But what does it mean for j to be in the cyclic group generated by A? How can I rewrite j? I'm not going to use n because n is the order, so I don't want to overload that variable. But I do know I can write it as a to some power. And what do I know about the power? So I'll use k here. That's what I want to show. But for just any cyclic group here, generated by A, what do the things in there look like? What kinds of powers? Where do my powers come from? What set? From my integers. So all I can say here is that I can write j as a to the k, where k is some integer power here. Okay, so I don't know which integer I have. I could have 1046 while n is the number 3. My goal is going to be to show I can have the same element written differently, written as a to a power between 0 and n minus 1. Okay, so here, we're going to be able to apply our division algorithm. So since n, the order of our element, is a natural number, this is going to work as our b in the division algorithm. We want to make sure it's a non-zero integer number. Really, actually, we want it to be positive. So we really want it to be natural here. And this power k is an integer. This is going to work as our a in the division algorithm. We can apply the division algorithm here. So that what relationship do I have between my n and my k, which is the old b and a? Which one can I write as the other, and what are the pieces here? So can I write a in terms of b, or can I write b in terms of a? A in terms of b. So here I'm going to be able to write k in terms of my n value. So I'm gonna be able to write it as k equal to some integer times n plus some other integer. So this is telling me I can find a q and an r in my integers so that I have this relationship. And what else do I know about my r? Yep, so I can say less than or equal to n minus 1 or strictly less than n. These mean the same thing since I'm working with integers. Right, so I'll even write it that way too. This is the same as saying it's less than or equal to n minus 1 here, which is really what we want. What we want to be able to show is I can rewrite a to the k as a to the r, because then my power is showing up in the correct place. It really is between 0 and n minus 1 is what I'm trying to show here. Okay, so here, if I look at my j that I know I can write as a to the k, because it's in my cyclic group, I now said I can rewrite my power as qn plus r. And ultimately, my goal is to get rid of the qn part and just have a to the r, then it lands in the correct place. So I'm gonna do some manipulation here to get rid of that piece there. So here, where I see that addition, I can separate it as multiplication downstairs. And where I see multiplication in my power, what can I do? Yep, I can see the multiplication in my powers as a power to a power instead. And I have a choice. I can either think a to the q, then to the n, or a to the n and then to the q. What do we think? Which order do we want to do? N then q, because we have information about what a to the n does. I don't know what a to the q does. So I'm going to write it in this order. What do I know about a to the n? Gives me back the identity because n is the order of a. Then the identity to any integer is going to give me back the identity. So I'm just going to get this a to the r here. Okay, so what we just did is we showed for any element j inside the cyclic group generated by a, we can rewrite j as a to the r, where r is between 0 and n minus 1, including both endpoints. So this is really saying I can find j within this within the set, right, where I go a to the 0, which is the identity, a to the first power, a to the second, all the way down to a to the n minus 1. Bless you. So using my division algorithm, right, I can take any of one of my powers, I reduce it mod the order of my element, of my generator, and that really lets me think about these elements in these smaller powers that are easier to work with. Okay, so what this just did, since we already had the first containment, is it told us that the cyclic group generated by A has exactly n elements in them that look like E, A to the second, all the way up to A to the n minus 1. And so here we can see, right, in particular, this is for n being the order of A. Okay, so our next goal is going to be to show if I choose any power here in this list, I really get distinct elements here. I actually can say more. If I take any powers, even if it doesn't show up in this list, I know they're going to be the same if they're equivalent mod n, right? Doing my powers mod n gives me the full information here. Okay, so we're going to do part B of number 2, deciding when these powers are this, or when these powers of A give us back the same element. So we'll go in the forward direction. We'll assume these powers are already A to these powers are the same, and we want to have some relationship between the powers I and J. So we'll start by thinking, just like we did last time, move one of my pieces over. So I'll get back the identity on the right-hand side. Oh. Come on. Okay, and what we're going to do is we're going to use the division algorithm now on the power I minus J instead. So by the division algorithm, I know I can find a Q and an R in the integers, where R is between 0 and n. And my identity element that I can write as a to the I minus j, I can now rewrite I minus j by thinking, what happens if I divide by n, right? I can rewrite this as qn plus r. Right, just as before, where I was using my power k and I was using my order n, I can do the same thing here, but now my power is I minus j. So I can rewrite that I minus j integer in terms of my n value. Okay, and in the same way we saw last time, that q to the n part is going to disappear. Okay. Okay, but we have the following here, right? I know that this R value is less than the order of the element of the order of A, but I just found a way to rewrite my identity as A to that power. But if n is the smallest positive integer to do that, what does that tell me about R? R has to be 0. It's not going to give me back a positive integer power. So my only other option is going to be this value of 0 here. Right, so what must R be? It has to equal 0 here. Okay, so this is telling me that I minus j, my R is 0, so I can write that as q times n. This is the same as thinking n divides this difference here, since everything I'm working with is integers, which is the same exact thing as thinking that these are equivalent to each other mod n. Right, so this is saying if I have a to 2 different powers and they're equal to each other, that can only happen when the powers are equivalent mod n, where n is the order of the element of my generator here. Okay, and we're gonna do the converse, right? We wanna go in the opposite direction. If I already know this relationship between I and j mod n, I wanna be able to show that these powers do really give me back the same exact element. So conversely, if I know n divides I minus j, that means I can write it as n times some integer. And so then if I think about a to the I minus j, I can rewrite that as n to the q, because a has order n, that gives me back my identity. So this is saying a to the I minus j gives me my identity. And I can multiply by a to the j on both sides. And this gives me a to the I equals a to the j. So we're really multiplying by a to the j on both sides to get this. All right, and this completes this portion of the proof, which really completes the 2-part proof that we have here, depending on the order of my element here. Okay, so the biggest takeaway we want to see here is that this theorem ends up giving us a link between the definition of the order of an element and the order of a group. But really, this is only going to work if I'm working with cyclic groups here. right? So it's gonna turn out that a group generated by A, so a cyclic group, is gonna have the same exact order as the order of the element. So as a group, as a cyclic group, the number of elements I see showing up is the same number as the order of the order of my generator here, right? And we'll see how does that theorem give us that information. But in the finite and in the infinite case, it's really giving me both pieces of information here. Okay, so if I think of my infinite case, my goal is to show the order of the element A is the same as the group generated by A. So what I'm gonna do is I'm gonna think, what happens when I have two integers in terms of my powers where they're not the same power? Is there any way I can get the same element back? If I can, that might be telling me that I don't have an infinite ordered group here. I really want to show if this group is infinite, no matter which power I take, if they're distinct, I will get back a new element here. So if I think back in my theorem, when my order is infinite, what do I know about the powers of A to the I and then the power of A to the J? If these are not equal to each other as powers, what does that tell me? If these cannot be equal to each other, unless the powers themselves are exactly equal to each other. Okay, so what this is saying is that my group generated by A, which I can write as A, my identity E, which is A to the 0, A to the plus or minus 1. I'm just going to write this as shorthand to go in the positive and the negative direction. A to the plus or minus 2, and so on. These are all distinct. So it has distinct elements. Because all of these powers are different, all of these elements are going to be distinct from each other. And so how many elements do I have in my set here? Infinite. One for every single integer power that's showing up, which is exactly the order of my element A, of my generator A. Okay, so for infinite ordered element, the group generated by that element will also have infinite order. And our goal is going to be to show when the element has finite order, that the same thing is true for its cyclic group. So let's say the order of A was n for some natural number. Then what the theorem told us, which was theorem 4.1, number 2, part A, told us exactly how we can write this group. I'm going to have the identity A squared, and where do I stop? A to the n minus 1. And by the same theorem, but part B, I'm able to show that every element that shows up in this set is going to be distinct from each other. Right? The only way these are equal to each other is if I look at the powers and mod n, they're the same. But here the only powers that are showing up are 0 up to n minus 1. And these are never going to be equivalent to each other mod n. So these are all distinct elements. And so the order of my group generated by A is exactly n, is exactly the order of my element A. So in either course, in either case, the order of the element completely determines the order of the group generated by that same element there. Okay, it turns out that this actually gives us a lot of information about orders of elements inside of our group. The first thing that we'll see here is if I know A to some power gives me the identity, it gives me some options on what the order has to be, right? In general, if I just know a to the k gives me the identity, I know this gives me a max value for my order, because possibly I can find a smaller power that gives me my identity. Here, I can cut the list by a lot. I can now say that whatever my order is, it has to divide the number k. So all I have to do now is study the divisors of k, and these are the only possibilities that I have for my order if I know a to the k gives me the identity. So it cuts down my list by a good amount. And again, I can think of this as saying k is a multiple of n, or we can say n is a factor of k. Right, we haven't looked at this divise definition, so if factors or multiples are easier for you to remember, you can think of it in this way instead. Okay, so we're going to assume a to the k gives us back the identity. And our goal is to show that k is a multiple of n, or that n divides k. But how can I rewrite e as a to some power? A to the 0. Okay, and now by theorem 4.1, number 2b, what can I say about these powers? They're congruent to each other mod n. Technically, the way that the statement was stated here, it's saying that n divides this difference, but that means exactly the same thing. And this is the part that we were trying to show, that n does divide k, right? This is the same as thinking k is equivalent to 0 mod n, which means that n divides k. Right, k is going to be some integer multiple of our n value here. Right, so again, as soon as I can write a to some power gives me the identity, I have a smaller list of possibilities for my order, not just 1 up to k. Now I look at that set and I delete the things that are not factors of k. If they're not factors, there's no way that I'm going to get back the order here. And technically, this is going to be an if and only if statement. As soon as I know I have n divides k, then I know a to the k will give me back my identity as well. Okay, so if n divides k, we've really seen this case already. I can write k as a multiple of n. And so if I take a to this power, I can rewrite it as q to the n. I'll do my trick with my powers to give me back my identity. So as soon as I know I have a number that's a multiple of the order, then a to that multiple power is going to give me back my identity. Right, so given the order of a is equal to n, and a to the k gives me my identity, these two things will now be equivalent to each other. If I know one, I know the other. If I know one is false, I know the other one is false as well. Okay, so this is saying, as soon as you know a to the k gives you the identity, you know that the order of a is some factor of k. So this is really giving you a smaller number of options. Than just the numbers that are less than or equal to k. Okay, so big takeaway here is we want to understand, when do our elements in our cyclic group repeat? In terms of our finite cyclic groups. This is going to be when the powers are equivalent to each other mod n, or never. So I guess I don't have to say this finite part. The never part is for when the group is infinite, or when the element has order infinity. Right, where n is the order here. Okay, so if I start with e to a to the 0. That's really my identity element. If I multiply by a, I get back 1, or a to the first power, then a to the second. I can go all the way around until I get a to the n minus 1. And if I multiply by a one more time, I get back my identity. So I do know a to the 0 gives me back a to the n. If I multiply by a one more time, I'll get a to the n plus 1, then a to the n plus 2, then a to the 2n minus 1, and so on. I'm really seeing this repetition here where I just care what is the power mod n. If it's equivalent to 0, it's the same as my identity. If it's equivalent to 1 mod n, then it's the same as a to the first. If it's equivalent to 2 mod n, then it's going to be equivalent to a to the second power, right? And I can do that for every single element. I can just think reduce the power, and it's easier for me to work with those specific elements instead. But I do get this cycle, I do get this repetition for every multiple of n that's showing up. Okay, so the next question we would want to answer, which is going to be what we start with in our next packet, is when do we get the same subgroup back out? If I have 2 different powers of a show up, how do I know when I get the same exact subgroup, right? In specific cases, I can tell you when the elements are the same, but the elements don't have to be the same for me to get the same exact subgroup. And so we'll look at that in our next packet here. But the answer is this can happen. Even if the powers are different, I can get back the same exact subgroup. And we saw this when we studied U10. Its subgroup, it has a subgroup of order 4, which I can write in 2 different ways. If I generate it by 3, I get 3, then 9, then 27, which I can rewrite as just 7, and then 81, which I can rewrite as just 1. So I get the elements 1, 3, 7, 9. But these will be exactly the same as the group generated by 7. If I did 7 squared, I get 49 or 9. If I did 7 cubed, I get 9 times 7, which is 63 or 3. And if I took it to the 4th power, I get back 1. But here we'll notice these elements are not the same, but I can write them as powers of each other. What power of 3 gives me back 7? It'll be 3. If I cube it, I get back 27, which is 7 mod 10. Okay, and if I look at what power of 7 gives me back 3, I get 49. Then 9 times 7 will give me 63. So I'll get back a power of 3 again here. Okay, this won't always give me back the same exact power, but there is going to be some relationship between the power and the order of the element. So here, the order of the elements are 4, and the powers that we were allowed to use here was the power equal to 3 here. So we'll see why in our next packet, why that relationship works, and what we can say more generally, right? So you can look through your recap. This recap is pretty short. But this is all that you need for your last problem. Just the very last problem needs this information. The second last problem in your cyclic section, you actually could have done before today. Yep, question. Not necessarily, because there could be more elements of order 3 in there, or they can be their own inverses. So just because they have the same order doesn't tell you that they have to have the inverses of each other. So I could have multiple different elements other than the element and its inverse generate the same group. So this doesn't get back to me immediately. Yeah. Yep, we will get that also. And that'll be one of the consequences that we have. A group generated by A is going to be the same exact thing as the group generated by its inverse. If I think integer powers, it's still going to be the same exact group. If I put a negative in front of that, those values, it'll give me the same exact elements there. Yep. Okay, so let's look at our new packet from today. So instead of looking at when do these powers give us the same elements, we're going to be studying the generators of cyclic groups, and we're going to decide when do these generators give us the same cyclic groups back. Okay, so we have our theorem already up here for us, and we'll go through the proof of this. We likely will not get to that today, but we'll get to that on Wednesday. But let's study what this theorem says, and then we'll actually practice it. We'll practice how to actually use that in our examples. Okay, so for our theorem here, we're taking an element A from a group G. And do I want, here I want, I said the order of n, but I have to be careful. Am I talking about the order of A, or am I talking about the order of G? Here I'm talking about the order of A, so I'm gonna make this explicit here. Right, we're saying the order of A is equal to n. We don't need to have that the order of G equals that same value there. So it can or it doesn't have to equal n, but here I'm really saying the order of the element is equal to n here. Okay, and now let's say I take any natural number k, and here I'm going to be able to decide which power is giving back the same exact group, or at least start to help me to figure that out. So it turns out here, if I look at a to some power, that power can be really huge, and it can be kind of hard to work with what the elements are. So what I can do, instead of looking at the power of k, I can look at the power of the GCD of n and k, and this will give me back the same exact group. It's also going to help us simplify to figure out what elements are actually in that group, because that GCD is going to be a divisor of n. So let's say I had a group of order or element of order 10. If I studied a squared instead, a divisor, I know I have a squared, a to the 4th, a to the 6th, a to the 8th, a to the 10th, which is the identity. But if I didn't have a divisor, if I said a to the 7th, it's much harder for me to decide what are the exact values that I have for my powers there. I have a to the 7th, then a to the 14th. But what is that really represented by in my group of order 10? So this is helping us to do a couple things. It helps us to simplify the power. It makes the power shrink. It also makes it a divisor. So it makes it easier for us to decide exactly what elements do we have here. So this is what part 1 is telling us. We can simplify any exponent in terms of generators using the GCD, and it still generates the same group. Right, and using a divisor or a factor will be simpler. So it won't just shrink the number, but it'll make it easier for us to tell what elements show up in this group. Okay, and then part 2 of this tells us exactly what the order of the element is. So in turn, it tells us exactly the order of the subgroup. So here, I'll take the order of A, which is n, and I'll divide it by this GCD, the GCD of the order of A, and this new power that I'm working with here. And again, we'll go through a bunch of examples so that we can see where's the n coming from, where's the k coming from, and how do we find out these pieces here. Right, but part 2 is much simpler. It's just immediately telling me what the order of this new power of A is, given that I know the information of the order of A, the base here. Okay, so in our example, let's think that we have an element A of a group, and that element has order 12. So the order of A is equal to 12 here, not the big group. So from our last theorem, what does this tell me about my group generated by A? How can I rewrite the elements in this set? Yep, A to the 0 up to A to the n minus 1, which is 11. And this A to the 0 is my identity. I know I have exactly N, oh, and that is 11. Exactly 12 elements showing up here. And I know that they're all distinct from each other. Okay, so our goal is going to be to decide what is the order of every single element here, just given the information about A and knowing what power of A we're working with. And again, we're going to be using this part 2 of our theorem, of theorem 4.2, to give us the orders of these elements here. Right, so here, what is my N value? 12. My N is representing the order of my base A. So here, my N is O. So it'll be the GCD of 12 and K. And K is just going to be the power that I have on my A here. So in all of these, I'm going to have fractions where 12 shows up upstairs and in my GCD. And so if we can figure out the GCD of 12 and that number, we just need to do this division, and it tells us exactly what the order of those elements are. So I'm just plugging in my 12 and all of these fractions as my numerator and as the GCD of 12, and then we'll fill in the second blank there. Okay, so let's start with the first one. Here, what is my K value and where do I find it? It's the power on A, which is just 1 here. So I'm going to plug in a 1 here. And so I'm going to do 12 divided by which number? 1, right? The GCD of 12 and 1 is exactly 1. So when I divide these, I get back 12, which I should get because I'm already assuming the order of A is equal to 12. But this still gives me the correct formula. The formula does work even when I have A to the first power here. Okay, let's look at what happens when I have A to the second power. All I'm doing is plugging in 2 in my GCD. And so what's the GCD of 12 and 2? 2. And so here I get order of 6. Okay, if I raise A squared to the 6th power, I get the identity. And this is really saying no smaller power is going to work. So I'm just going to continue with this, and this will be good practice finding our GCDs. What's the GCD of 12 and 3? Yep, so I'll get back 4. The GCD of 12 and 4. So I get back 3. The GCD of 12 and 5. This is just going to give me back 1. So the ones that we saw so far, all of those were factors of 12. So the GCD is just going to be that K value. If I have a number and one of its factors, that factor is going to be exactly the GCD. It's the smallest thing that they have in common. But here, my 12 and 5 have nothing in common. So these are relatively prime. My GCD is going to be exactly 1. Okay, next up I have 6. Again, another factor. So my GCD is going to be exactly 6. So when I divide these two, I'll get back 2. And I keep going. What do I get for my GCD of 12 and 7? 1. So my order is 12. My GCD of 12 and 8. 4. They both have a 4 in common and nothing more. Oh, so I'll get 12 over 4 or 3. Then I'll have the GCD of 12 and 9. What's that? Okay, so I'll get back 4. GCD of 12 and 10. Yep, so I'll get back 5. GCD of 12 and 11. Okay, so I get back 12. Oh, thank you. I knew that number looked weird. Okay, and last one, the GCD of 12 and 12. Okay, which gives us back 12. And what is A to the 12? That's our identity. This should be the only, oh, and I messed up this thing. Yep. This is the only element that should have order 1, right? So this formula really does work for any power of A that I have showing up here. Okay, so this actually gives me some more information. Which elements or which powers give me back the group generated by A? And how do I decide that? So before you tell me, how are you deciding? What are you looking for? Order 12. I'm really looking which elements have the same order as A. All of these are gonna be subsets of the group generated by A. And if they have the same exact order, if they have the same number of elements, they have to be the same exact group. So here I have 4 different places where I have order 12. So what this is telling me is that the group generated by A is the same as the group generated by 5, by 7, and by 11. There's a lot more information that we can actually see here. If I think about the factors of 12, I should get back 1, 2, 3, 4, 6, and 12. We're seeing all of these show up as orders of at least one of these elements, right? I see 1 for my identity. I see 2 showing up once, right here for 8 to the 6. I see 3 show up a few times. I see my 4 showing up. I see my 6, and I see those 12 showing up. This is something really special about our cyclic groups. It turns out we can completely determine what the cyclic groups are going to look like, what subgroups they're going to have, how many you'll have of each kind, of each order. We can completely determine all the information about our cyclic groups just by knowing the order here. So this is really just going to be helpful when I have finite order. When it's infinite, things can go a little bit more wacky. So we'll focus in the rest of this packet on how do we figure out that information? How much more can we find about this? But in our next step here, what we want to do is we want to actually prove this theorem. And then we'll see what other consequences do we have? What other information can I tell you about any cyclic group that you give me? Okay, so we won't have enough time to go through the full proof. So let's just talk about what are the pieces to be able to show these statements. And then we'll go through more detail on Wednesday's class. Okay, so the first thing we have, we'll focus in on number 1 here. Our goal is going to be to show these sets are equal to each other. So how do we show sets are equal? Double containment. I want to take something from one of my sets and show what's in the other, and vice versa. It turns out that we can actually do this a little bit faster because we're working with cyclic groups. So don't mind the first part here. Let's just look at part 1, what we're trying to do. We're trying to prove this with double containment. And it turns out, I want to delete one piece of this. It turns out if I just look at my A to the K, so not my group here, I have some typos. This should be an element of, this should just be the element. It turns out that if I can show the generator of A to the K is in this group, then I know I get a subset here. And if I know that the generator of this one here is inside that group, I know that the whole group generated by it also has to land inside of there. Right, so it's much easier than my double containment. I can just show the generators have to land in the correct places, not just any element in there. The generator is going to be enough here. Can we see why this would be enough? If I know my generator is inside a group, why do I know the group generated by it has to be in there? What property can I use here? Closure. As soon as I have one element in it, I know I can multiply by itself and land back inside the set because it's a group. So if I do that any number of times, I should still land inside my group here. So here, just because of closure, and because I know these cyclic groups really are groups, if an element is in the group, then so are its powers, really all its powers. Okay, so in part 1, that's what we're going to do. We're going to show that the generators are inside of all of our cyclic groups here in both directions. We'll need this fancy theorem called Bezout's theorem. We'll go over what that means next time. And then let's think about our part 2. Our part 2 is about an order. Our goal is to show the order of a to the k is the specific number, the specific ratio that we have here. How do I show that? How do I show an element has a specific order? So let's say I wanted to show a had the order 3. What do I do? Yep, so I want to show a to that specific number does give me back the identity, and no number less than that is going to work for my power to get back the identity here. So that's going to be our goal for that piece there. But even before that, we can do a little bit of work to simplify this so that we don't have to be working with a to the k. Let's remember here, if k is any power, this is going to have the same order of which group? What did our last theorem say? The order of the element is going to be equal to the order of what? Of the group generated by that element. So here I can think, what's the order of this group? And that'll give me back the order of the element. And then part 1 is telling me that this group is exactly the same if I change my power instead. If I raise it to the power of the GCD of n instead. And by the same logic, the order of the cyclic group is the same as the order of the element itself. So here, instead of showing a to the k has a specific order, I'm going to end up showing that a to this divisor has that same order. This is the part that we're actually going to show. So if I want to show an element has a specific order, right, that's what I want to do in this piece here. I need to raise that element to that power, show I get the identity, and then show that no matter which power I take less than that number, I'll never get back the identity. It won't give me back. This really is the smallest positive integer that has this nice property here. Okay, and I'm going to rewrite a piece of this. We're not going to do the proof of this. I'm just going to set this part up. I'm going to call this GCD of n and k. This is the number d. This is the part I wrote up here that we ignored, just to make it easier for us to write. This is really saying if I take this element a to the d, I want to be able to raise it to n divided by that same number and show I get the identity. And I want to be able to show this is the smallest power I can raise it to and still get the identity. So I really want to show this n over d is the smallest such natural number to do so. Okay, so this is what we're going to do on Wednesday. We're going to look at both of these parts. We're going to show the generators land and these other cyclic groups to show we get containment, really to show double containment, and these groups are really the same, even though the powers are different. And then we're going to talk about the order of these elements of these groups. But really, we're going to think about a to that reduced power to the GCD, show it has the specific order we want it to have by showing when I raise it to that power, I get the identity, and any smaller power is not going to work. It's not going to give you my identity back out. Okay, so these proofs are pretty involved. This level of proof is not the type of proofs that you'll see on like homework or on exams, but it does give you good intuition on how do I prove any one of these pieces. If I just wanted to show order, what did I have to do to be able to do that? If I wanted to show two groups were equal to each other, what are the different ways that I can do that? So if this feels overwhelming, that's okay, right? The goal was just to understand step by step, how are we getting there? If you feel like you couldn't have done the whole proof on your own from scratch, that's perfectly fine. I'm not expecting you to be able to do that, which is why we're really breaking these up into smaller and smaller pieces that are much more manageable for us to understand and be able to digest. But after we're done with our proof, we will go through some corollaries that we get from that, some nice consequences that we have, and then actually working with some examples to see how can we use this in practice? What can I actually say about this specific group if I know that this theorem is true here? Okay, but if we don't have any questions, then I'll see you guys on Wednesday, and we'll continue on with this packet.